In this video, we're going to take a look at the last topic that's related to these parametric curves that we've been studying. So far we know how to find the derivative or a higher order derivative of a parametric curve, and that gives us slope and so forth. And then we learned how to compute area, right? Area that's bounded between a parametric curve and either the x or y axes. And now we're going to take a look at arc length. So just a reminder, again, always nice to start with the picture. So let's say we have a nice differentiable curve, and this curve could either be given explicitly y as a function of x, or explicitly x as a function of y. And let's say it's the former, y equals f of x, and we know the x-axis, the limits on the x-axis, x equals a and x equals b. Then we can find our arc length by integrating with respect to x, and it's the definite integral from a to b. And then we have the square root of 1 plus our first derivative squared dx. If it's the latter and it's x as a function of y, and again x is a differentiable function of y, then the arc length formula becomes this. Now we need our limits on the y-axis, so let's say that's c, and then that's d, and then the arc length differential becomes the derivative of x with respect to y. We square that, we add 1, we take the square root of that entire quantity, and then we integrate with respect to y. All right, so there you go. So we've used these formulas in the past. The question is, how does this convert over now if we have a pair of parametric equations? Again, our x variable is a function of t now, and similarly our y variable is a function of t. So what happens in the parametric case? Well, if you think about it, we don't necessarily have to go all the way back to first principles here, because we now have a way of expressing dy dx for our parametric curves. So just so that it's not too tedious to keep writing down the definite integral and the differential, well, what I'm going to focus on is just this part, right? It's just going to be this part. And the reason why I'm just going to focus on that part is because we know when we switch over to the parametric form, then you'll have a value of t that gives you that x, and it's the same value of t that will give you that y. And then similarly, we'll have another value of t that will give us b, and similarly that value of t will give us d. So the limits are converted over really easily. The question is, what happens to our arc length differential? So recall, right, we have our formula for dy dx, right, for a parametric curve. It is dy dt divided by dx dt, provided that dx dt is not equal to 0, right? I don't know, that looks like recalling. No, it's just recall. So we have this formula. So let's just do this, right? Let's just go ahead and plug that formula, plug this fraction in for dy dx, and we see what happens. Let's see what happens when we do this sort of a conversion, right? So this implies that the square root of 1 plus, now let's plug in the expression for the derivative, dy dt over dx dt, and that whole quantity is squared, and then that's also multiplied by dx. All right. So let's see what happens. Well, we know how to square a fraction. We can square the numerator and the denominator. So I'm going to write a pretty big radical here. And then this will be, and I'll write it like this. dy dt squared over dx dt squared. And then this is times dx. I guess I have a lot of empty space there. That's fine. So now under the square root, we have 1 plus this fraction. Well, let's write this as a single fraction. In order to write what's under the square root as a single fraction, we need the common denominator. So if I treat this as 1 over 1, then I'm going to multiply the 1 over 1 by the quantity dx dt squared, right? So it's going to look like this. It's going to be dx dt squared over dx dt squared plus dy dt squared over dx dt squared times dx. We can't forget the dx there. All right. Well, let's see what happens. So now we can write this. So now that we have our common denominator, this can be written as a single fraction. So it will be the square root of dx dt squared plus dy dt squared. I have no idea why I'm saying it that way. It's like I'm trying to make a song out of it. Dx dt squared and then times dx. Now we're going to use some properties of square roots here. So the first one is this, just as a reminder, the square root of a over b is equal to the square root of a divided by the square root of b, provided that b is not 0, right? And if you notice, we already made that assumption up here that our dx dt is not equal to 0, so that's good. All right, so we're going to write this as the square root of dx dt, that quantity squared, plus dy dt, that quantity squared, and then over this another square root, and then under that it's dx dt squared, and I still have my dx there. Okay, so under the square root in the numerator, we have the sum of two perfect squares. And we know that those expressions are not easily simplified. So there's not much I can do with this. But in the bottom, I have the square root of a perfect square. And in a perfect world, these would always cancel out, but they don't always cancel out. However, we are going to make an assumption about our parametric curve to say that dx dt is always positive. So if we make this assumption that dx dt is always greater than 0, and what this means is that the parametric curve, it's like it's oriented towards the right. So in other words, if the rate of change of x with respect to t is always positive, then it means that x is always increasing. So in other words, the curve is either going that direction, that direction, that direction, something like this, right? So that's a pretty important assumption that we're going to make, and it allows us to simplify this expression quite a bit more, right? Because look what's going to happen under this assumption. So if dx dt is greater than 0, then the root and the square in the denominator will cancel out. So we will have this, but nothing cancels out in the numerator because we have the sum of perfect squares, right? Which in itself is not necessarily a perfect square, right? So yeah, in the denominator, we're left with dx dt, and then we have our dx there, right? Now think about what this is saying. This expression is saying, okay, take this radical and divide it by this fraction. Well, now, again, think of how we divide by a fraction. We multiply by its reciprocal. So I'm going to keep the that radical as it is, right? That's not going to change. Looks like this. And then I have my dx, that's not going to change. But now instead of writing divided by or over the quantity dx dt, I'm going to multiply by the reciprocal. So I'm going to flip over the dx dt, it becomes dt over dx, and, oh, sorry, I wrote t there. So dt dx, and what happens is these little differentials, they go away. So look at what happens to our arc length formula now. Once we convert it to the parametric form, this is what the arc length differential is. In other words, this is the thing that we're going to integrate from t0 to t1. So it's the square root of this big quantity, dy dt squared, times dt, right? So let's kind of summarize it now and say, again, under the assumptions that we've made, we have a nice differentiable parametric curve, so no sharp corners or anything like that. And with the added assumption that dx dt is always positive, then the arc length formula becomes this. It's the integral from t0 to t1 of this expression right here. So it is dx dt squared plus dy dt squared, and then we integrate that with respect to t. All right, so let's go ahead and put this in a nice colorful box, because that's a formula that we're going to use, right? So what's left? Well, you're probably asking for some examples, and lucky for you, I have a couple examples set up. All right, so let's look at some examples. The first one, again, I'm just going to state the parametric curve and the range of values for t. So basically giving you t0 and t1, and then we're just going to set up and evaluate. So here's our curve. I'm going to write it in the ordered pair. So let's say the x coordinate is 3 cosine t, and the y coordinate is 3 sine t, right? So that's our parametric curve. I'm just giving it in an ordered pair. So basically that's x of t, that's y of t. And let's say this goes from 0 to, instead of 2 pi, which, would be one full revolution, let's go to pi, right? And this is actually the parametric, one parametric way of defining a semicircle that goes from t equals 0 to t equals pi. In fact, I can sketch that over here pretty easily. So let's say here's our origin. Now the coefficient of 3 means that the radius of our semicircle is 3. So it's going to go to no greater than x equals positive 3 and no less than x equals negative 3. And because you're going from 0 to pi, you're going to start out here, and then it's just going to be traced out like this. Ah, that's a pretty good sketch, if I may say so myself, right? So that's the curve that we have here. And essentially we want to find how long that is. So when we're doing our arc length, we want to figure out the length of this, right? Well, I'm going to say this. I'm not going to do it geometrically, but there should be a formula that involves circles that you might be thinking about and saying, well, why do I need to use calculus for this if I can just apply that formula? And here's a big hint. It has to do with the circumference of a circle. Well, in this case, half circle. But we're going to use calculus, right? So let's go ahead and set everything up. So I'm going to write down the derivatives that we need. So dx dt, when I differentiate 3 cosine t, I'm going to get negative 3 sine of t. When I differentiate 3 sine of t, I'm going to get 3 cosine of t. So that's our dy dt. 3 cosine of t. Pretty good so far. And then let's look at what the arc length formula says. It says we have to square both of these derivatives, add them together, and then take a square root. Well, let's just do that all in one operation. Since these, or I should say one step. There's several operations, but we're just going to do it in one step because these derivatives aren't very difficult, right? So here we go, -3 sine of t, all of that squared, plus 3 cosine of t, all of that squared. Now, I'm just doing the square root part, right? I'm going to simplify this as much as possible, and after I simplify this as much as possible, then we will go back and use our definite integral, right? So it's not that I've forgotten my integral or my limits or my differential. I'm just focusing on the square root right now. All right, so we have our square root. Now here's another property of I guess exponents that we're going to use. So remember, if you have a times b to the n, that's equivalent to a to the n times b to the n. So that's what we're doing here. In other words, remember, we have to square the coefficient and we got to square the trigonometric functions. So -3 squared is 9, and then sine of t squared is, well, sine squared. And then similarly, when we square the other term under the square root, we will get 9 cosine squared, right? Now, when you look at this expression, you feel like some things should really simplify, right? You feel like this should simplify quite a bit. And it's going to simplify because under the square root, we now have a common factor of 9. So I'm going to factor out a 9, but that leaves sine squared t plus cosine squared t. And I don't know how many times we've used this identity when we were doing all our trig stuff, but that expression that's inside the parentheses, this is equal to 1. And what that means is that our arc length differential, the thing that we're going to integrate, turns out to be a simple constant. So it's the square root of 9 times 1. The square root of 9 is 3. So let's write down now the arc length integral in its simplified form. Our arc length is going to be the definite integral from 0 to pi, right? So we're using these two limits, right? 0 to pi. And then this is what it simplifies to. We're just going to integrate 3 dt. Right? So it really doesn't get any easier than this. And again, this sort of resulting integral isn't completely new to us. We've seen problems. In fact, we've seen arc length problems where when we set it up in the, let's say, the explicit form, our derivative comes out to be a constant, and it's a relatively easy problem. Something similar happens here, and it's because of that wonderful trigonometric identity. So now let's find our antiderivative with respect to t. So this is 3t, and then we're going to use our fundamental theorem and a little bit of magic. We have 3 pi minus 3 times 0 is 0, so we end up with 3 pi units, right? Now, again, I am not going to do the work. I want you to think about it, but think about how you could have used the circumference of a half circle to come up with the same value that will give us the length of this half or semicircle. All right? All right, so that's our first example. Let's do another one that isn't going to work out as nicely because we're not going to have a nice trigonometric identity that we can use, but we'll still figure out a way. So here's the parametric curve. The x equation, let's just say it's 2t. The y equation is like 2/3 t to the 3/2. There we go. And in this case, let's say t goes from 0 to 1. All right. So this curve is, it's not difficult to sketch, but it's a little bit harder than, sketching the semicircle. So I'm not even going to try to sketch this, because again, what calculus allows us to do with these formulas and these processes, it allows us to solve problems without the aid of a visual, right? So it's just kind of abstract way, like, what does this look like? I don't really know, right? But let's go ahead and work through the process. So dx dt, so the derivative of the x equation is just 2. dy dt, this one we'll have to do a little bit of the power rule. Well, technically we did the power rule here, but it works out so nicely just getting a constant. Here you'll have 2/3 times 3/2, which is 1. And then you'll have times t to the 3/2 minus 1, so that's 1/2. So again, not very difficult derivatives. So let's just write this as t to the 1/2, right? Or if you'd prefer, square root of t. So now let's set up the arc length formula. Again, I'm going to start with the radical and then see what we can do with it, and then eventually set up our definite integral. So it's the x derivative squared, so that's 2 squared, plus the y derivative squared, so that's root t squared, and then under the square root, so we have the constant 4. The square of the square root means we're just left with t. Here we go. And there we go. And it turns out this cannot be simplified anymore, right? There is no property of roots that allows me in general to take the root of a sum, right? So we're kind of stuck, and there is no nice simplification, right? So this is what we're going to have to integrate. So let's set it up and then think about how best to integrate this, because right now we do have a plethora of integration techniques. Surely one of them should apply to this, otherwise why would I be doing this problem, right? Well, it turns out we don't really have to overthink this too much, right? Because we can use a standard u sub, right? So I am going to let u be 4 plus t. That means du is dt, so that works out nicely. And then let's switch our limits of integration. So when t is equal to 0, u is 4 plus 0, so that's 4. And then similarly, when t is equal to 1, u is 4 plus 1, so that's 5. So with our u sub, we've converted our definite integral, and the limits are now 4 to 5. Under the square root, we have a u, which I can then write as u to the 1/2, and then my dt is just replaced by du. So now we forget about everything that came before this, right? Forget about all the setup, forget about this definite integral right here. Just do this problem, use our FTC, and we're good to go. So power rule now for antiderivatives, add 1 and divide by the new power. So that would be 2/3 u to the 3/2, and then that's evaluated at 4 and at 5. So we'll have 2/3, and then we'll have 5 to the 3/2 minus 4 to the 3/2. Now 4 to the 3/2 is a nice integer. 5 to the 3/2 is an irrational number, but it can be reduced like this. This is 5 root 5, and then 4 to the 3/2, it means you take the square root. So start with the denominator here. Take the square root of 4, that's 2, and then 2 cubed, that's 8, and then we have this. And then, apart from getting some decimal approximation, which I'm not going to worry about right now, you can distribute the 2 over 3, and you will have 10 root 5 over 3 minus 16 over 3, and then this would be units. I just realized that in our first example, oh yeah, I did write units. There we go. So that's the length of our half circle, 3 pi units. And here is the length of this curve that I don't even know how to describe it, but it's some nice differentiable curve. And here is its length. And there you go. So now we have looked at how to compute slope, areas, and arc length for all our parametric curves. So hopefully you found this interesting and informative, and I look forward to seeing you in the next video.